In this first example, we want to solve the following system of linear equations, and we're going to do this by graphing. I'm going to sketch a graph of both x plus y equals 4 and 2x minus y equals 2 and see what happens. So for the x plus y equals 4, it has a y-intercept of 4, 0, and also an x-intercept of 4, 0. So, I'll try to do as good a sketch as I can, but we have the line that goes through these 2 points, and it looks like this. Now, we also want to graph the other line, which I'll do in red. Maybe I'll write that one differently. So off to the side, if you have 2x minus y is equal to 2, that's the same thing as 2x minus 2 is equal to y, and that was just by subtracting 2 from both sides and adding y to both sides. Maybe writing it in a more familiar y equals mx plus b form from left to right. I see that the slope is 2 and that the y-intercept is negative 2. So let's see, negative 2 for the y-intercept. A slope of 2 looks like this. Oh, I can already see that we're going to get this point here as well, and if we draw the line that goes through these points, this is our graph. So something very special happens with these two equations, and that is namely they meet up at this point. It looks like that's 2, 2. So this is what it means to be a solution to a system of linear equations. It's a pair x, y that makes both equations true at the same time. So when I say solve it graphically, we're just looking for where the two graphs actually intersect each other. We can plug this in to see why it works. So like if you have x plus y is equal to 4, putting 2 in place of x, putting 2 in place of y, and asking is this true? It is true, 4 equals 4. But not only does it work for x plus y equals 4, it should also work for 2x minus y is equal to 2. So again, putting 2 in place of x and 2 in place of y, we get 4 minus 2. Well, is that 2? It is. 2 is equal to 2. The point 2, 2 makes both equations true at the same time. And this is what we mean by a graphical approach. Now, from this point forward, I really don't want to use a graphical approach. I mean, there should be a nicer way to do this without sketching the graphs every single time. So the other thing I list in the example is use the substitution method to solve this to see what that looks like. All this means is we focus on our two equations, and the goal is to eliminate either the x or y to reduce this to an equation with one variable. So what does that mean? So here's what I'm going to do. I'm going to look at the equation 2x minus y is equal to 2. Well, we already solved it for y, so that's over here. Y is equal to 2x minus 2. So let me write that off to the side. This is the same thing as y is equal to 2. Y is equal to 2x minus 2. What I'm going to do is take this y value and put it into the y in the first equation. So that's what we call it the substitution method. We're plugging it back into the original expression. So I'll do that work over here in black. So I have my first equation, which is x plus y is equal to 4. For my second equation, I know that y is equal to 2x minus 2. I'm going to substitute that in place of y. So x plus 2x minus 2 is equal to 4. So what this does is give us one equation with one variable which we can solve for. So let's see. That's really x plus 2x minus 2 is equal to 4, or 3x minus 2 is 4. Adding 2 to both sides, we get 3x is equal to 6. And dividing both sides by 3 gives me x is equal to 2, which is great. That actually matches up with the x value that we already solved for. Now, we also need to know, well, what's the corresponding y value? But the nice thing is, you can use any equation to figure that out, provided that there's an x or a y in it. So I'm going to go back to this very first equation. I'll put 2 in place of x, and solve for y. So that's 2 plus y is 4. I'll subtract 2 from both sides, and, well, what do you know? I get y is equal to 2. So x is 2, y is 2. That means the point 2, comma 2 is the solution. So we already know that this is the case, but this is just another approach you can take where you don't actually have to refer to a graph. You can simply work with the two equations themselves. Example 2 here is going to illustrate another really powerful method that's very quick for solving certain linear equations, a system of linear equations. This one's called the addition method, and that name just means you're going to take your equations and add them together in some way. So I'm going to rewrite these equations. We have negative 3x plus y is 5. I just want to line it up a little bit more carefully, but below that I have 6x minus y is equal to negative 11. Well, if I add the left sides together and also add the right sides together, well, that should give me an equation that combines both and yields something that still is true. Let's see what happens if we do that. So we'll start with, we have negative 3x plus 6x. Well, that's positive 3x. And here's why this method is going to be nice in this problem. We have plus y and we're adding a negative y. You don't even need to write it down, but that's 0. Maybe I'll put it there for emphasis. Okay, now we have that's equal to, all right, I have 5 plus a negative 11. Okay, that's negative 6. So this is actually really fast. I mean, this is the equation 3x is equal to negative 6. If I want to get x, I would just divide both sides by 3, which is negative 2. So there's no graph that was necessary. There's no plugging into another equation. It was simply just noting that, oh, you can just add them together. Let's see what happens. Now, we still don't have the corresponding y value, but we can use any equation that has an x and a y to do that. So I'm just going to choose the very first one, which was negative 3x plus y is equal to 5. I'll put negative 2 in place of x. So that's negative 3 times negative 2 plus y is 5. And from here, there's only a y value that I can solve for. 6 plus y is 5. And subtracting 6 from both sides gives me y is equal to negative 1. Here's your solution. The solution is x is equal to negative 2. And y is equal to negative 1. Or if you'd like, you could write it as negative 2, negative 1. So this was very fast. It worked out that just by adding these equations together, it canceled one of the variables very quickly, and we were able to arrive at our solution. It won't always be this simple, and we'll see that in the next example. So you'll notice that the system of linear equations in example 3 is almost identical to the one in example 2, except it's not minus y anymore. It's now plus 2y, but all the other numbers are the same. So I don't know if this is going to work out nicely. I just wanted to make something up to see what it would look like if we just changed one of the numbers. So let's see. I still want to use this idea of the addition method, where I'll add the equations together to get my answer. Unfortunately, if you add this part, you still get 3x, but if you add this part, you get 3y, and we didn't cancel x or y. When using the addition method, you want to cancel either x or either y, and by adding, we can't do that right off the bat. However, we can multiply both sides of any equation by some number so that when we do add the equations, one of the variables will cancel. And there's multiple ways to do this, so I'm just going to choose one way. When looking at this first equation, if it wasn't plus y, if it was negative 2y, that would be perfect. I would add these two together, and I'd get 0, kind of like in the last example. So I just want to somehow get a negative 2 here, and there's a very simple way to do that. I'm going to take the first equation, and I'm going to multiply both sides by negative 2. I'm just going to put in what I want. And I'm going to be careful that I make sure I adjust every other term appropriately. So if I multiply negative 2 to every term, I'm going to get well, now this is going to be positive 6x, this is going to be negative 2y, and this is going to be negative 10. So let me write that down. That's, the first equation becomes 6x minus 2y is equal to negative 10. This equation must be true since I did the same thing to both sides of the equation. So I'll copy the same equation down below it. 6x plus 2y is equal to negative 11. So I just left that one alone. You could multiply that by something as well, but we don't really need to do that here. I'm just noting that, oh, okay, well, if I add the left sides and the right sides, this one works out really nicely in that it cancels the y's. We get 12x, the y's are gone, but now we get, this is going to be a mess, but we get negative 21. And when I divide both sides by 12, I get a messy answer, but it's negative 21 over 12. There's a factor of 3 that I can cancel from both the numerator and the denominator, which would give me negative 7 over 4. So I'll use the simplified answer. So we're not quite done yet. We have to solve for y. And again, you can use any equation that you'd like to do that. And I'm just going to go right back to the very first one. So I'll use negative 3x plus y is 5. So I said this question's going to be messy just because I think we're going to end up with a fraction for our answer that might take a little bit of work to get. I'll put in negative 7/4. There's nothing I'm putting in place of y, which is good. I want to be able to solve for it. And that's all I need to do is solve for y. Okay, so that's going to be negative 21 over 4 plus y is 5. So continuing my work, I'll add 21/4 to both sides, and I get y is equal to 5 plus 21/4. All right, I need a common denominator of 4, which means I'm going to multiply the 5 by 4, so I get 20. And y is equal to 41 over 4. 2 and 4 don't go into 41. I think we have to leave the answer as that, but here's our answer. I have both an x and a y value. My x value is negative 7/4. My y value is 41/4, and this is my final answer. What this means is, if you were to graph these two lines, they would intersect, and the place that they intersect would occur at this point over here.